Yeah, thanks, Permit. So next we have a joint talk by Adria Gascon, Kallista, Bonawitz, and Peter Kairouz. Thanks a lot, guys. So they are all currently at Google. They have done tremendous work in federated learning and differential privacy. Also, like Kallista was also part of the paper that introduced federated learning. So today we're gonna listen to the recent research in federated learning. And we are looking forward to it. So you can start.
Great, thank you. So I'm happy to be here today talking to you about privacy and federated learning at scale. I'm Kallista, and I'll be co-presenting with Adria and Peter today, but really we're representing the work of many of our colleagues at Google and beyond. So today we're talking about federated learning, what it is, and how it relates to privacy and machine learning. We'll talk about how we distribute trust by running cryptographic secure aggregation at industrial scale, and by combining it with randomization to achieve distributed differential privacy guarantees. And we'll conclude by highlighting some of the important challenges and open opportunities in federated learning.
Kallista, sorry to interrupt you. I think there's some like, are you pressing the keyboard or is it from your microphone? There's some noise coming out.
A click?
Yes, something like a click.
Right. Let's see if it's, I don't usually use these headphones, so maybe it's that.
I think now it's good.
Okay, great, thank you. All right, so federated learning and privacy. Federated learning is a machine learning setting where multiple clients collaborate in solving a machine learning problem under the coordination of a central service provider. So each client's raw data is going to be stored locally and not exchanged or transferred. Instead, only focused updates intended for immediate aggregation are used to achieve the learning goal. Now, reasoning about privacy in a complex system like a federated learning system requires understanding precisely what pieces of information each actor in the system will have access to. In fact, every machine learning system that operates on end user data, whether it's centralized learning, federated learning, or some other decentralized learning paradigm, has a variety of actors playing different roles in the system, and each actor requires a different view of the multi-user data set. So end users are going to be generating the data through interaction with one or more devices. And we need to ask, what could an adversary with access to one of those devices observe? Some of that information is going to flow across the network, and we need to know what can be learned by observing the network transmissions. Often servers assist in the collection and processing of user data, and we have to ask what can be learned by observing that process. Machine learning engineers need to monitor and evaluate the models as they are being trained, and we need to know what can such a machine learning engineer learn through this process. And finally, fully trained and evaluated models will be deployed to power potentially billions of end user experiences. And we might ask what can be learned from observing these deployed models. Now, federated learning's architecture comes with built-in data minimization principles that limit access to information for each of these actors, minimizing data exposure on each device, collecting only focused data to the server, and using anonymous ephemeral strategies to collect that focused data, and releasing data only in aggregate, both to ML engineers and when deploying the final models. Federated learning's privacy principles can be strengthened and rigorized through the use of complementary data anonymization and minimization technologies, such as secure aggregation, differential privacy in all its flavors, model auditing techniques, and so on. So let's take differential privacy as an example. It can be applied in a centralized setting. You would clip each client's contribution to bound that user's influence, and then you would add noise on the server to prevent the model from overfitting to any particular client's contribution. And this ensures that the trained model and the model iterates along the way do not contain too much information about participating clients. So that applies to some of the roles. But now that requires that the clients trust the server in adding noise, which may not always be desirable depending on how much you trust the server as an actor. So instead of applying DP centrally, both clipping and noising can be applied locally on the clients. Unfortunately, as shown in the DP literature, this generally leads to poor performance. So in this talk, we ask if we can somehow combine the best of both worlds. And the good news is, the answer is yes. We can use a version of differential privacy called distributed differential privacy, which offers privacy guarantees and trust models very similar to local differential privacy, while retaining the high quality model performance of central DP. Ideally, we are going to look for a solution where we provide some formal DP guarantees as soon as data is collected at the server, and then we progressively strengthen our guarantees as the attack surface gets bigger. That is, as we move from the servers having very few system administrators through the larger number of ML engineers, and eventually provide the strongest guarantees for the deployed models. To achieve that, we need to look carefully at how we distribute trust among the actors in our system. There are many approaches to trust distribution. For example, even with a simple subproblem like aggregation, vector summation, we could distribute trust by establishing a trusted third party to do the aggregation for us, or to at least shuffle the to the aggregated values. Or we could use trusted execution environments like secure enclaves as a source of distributed trust. Or we could distribute using cryptography, and that's what we'll focus on in this talk, a version of distributed privacy that uses cryptographic secure aggregation. To achieve our goal, we need to carefully mix differential privacy with secure aggregation at scale. So the rest of the talk will be divided into two parts: how to design a secure aggregation protocol that scales to large models and millions of clients, and how to properly mix differential privacy with secure aggregation. And with that, I'll hand the talk over to Adria.
Can you hear me well?
Yes.
Okay, let's get going then. So in this part of the talk, as Kaylee said, we will discuss a concrete secure aggregation protocol that intuitively satisfies what's stated here and what one would expect. That is that the server collecting all the model updates in the context of FL learns nothing but the sum of those vectors and no individual data whatsoever. And this will be the case even if some users behave maliciously and some drop out. The previous promise is, as you would expect here at Crypto, made precise using the standard real versus ideal paradigm of MPC. And for our protocols, we show that every adversary controlling a given fraction of the clients and the server, shown on the left, can be simulated in the setting where a trusted aggregator is available. This idealized setting shown on the right. And this shows that any leakage about honest inputs that come from the aggregation functionality itself it's inherent to the functionality and leaves out of scope things like enforcing input validity, because that's something that, something like choosing their input is something like that malicious clients can do themselves, right? So we cannot prevent them from doing that in this setting. So although I won't discuss the proofs of the protocols that I'll describe, they are secure in this very concrete setting used in MPC, and the details are in the papers that I'll cite. So let's make our setting and goals concrete. We're in the FL setting, right? So we have a single server and n clients in our star topology, and each client holds a very long private vector, which you can think of as having length 100,000 or 1,000,000. And the goal here is for the server to obtain the sum of all private input vectors of all clients, even if up to a given number of dropouts happen. And this maximum number of dropouts is expressed as a fraction. So you can think of delta as 1/3. So if less than 1/3 of the clients participating in the protocol drop out, then the server should obtain the sum of the surviving clients. And if more than that number drop out, then the server gets on. Now, in terms of security, the server should learn only the sum, even if it colludes with up to a gamma fraction of dishonest clients. And you can think of that as 1/5, for example. And in terms of related work, although there have been several recent works on secure aggregation, I will be referring mostly to the CCS 2017 paper, this one, as the protocol that I will present is inspired heavily by that one. So I will be talking during the rest of this section of the talk about this paper presented at CCS last year and co-authored with Kaylee, James, Mariana, and Tancred. And while the previous CCS 2017 secure aggregation protocol scaled to roughly 1,000 clients for production size FL models. Those same client costs allow for going over 1 million clients with this new protocol. Okay, and we have protocols for both semi-honest and malicious security. And in that same paper, we propose a reduction from aggregation to shuffling that Kaylee will talk about later. Okay, so let's get into this setup and guarantees. So in these kind of protocols, it is common that the protocol starts by having all clients share their public keys with each other through the server. And from then on, we can think of the server as a private channel that lets clients communicate privately by relaying messages among themselves. And only exchanging public keys with every other client requires linear communication per client. And that ends up being a limiting factor in handling very large number of clients. So the work that I will present boils down to reducing the number of clients that each client in the protocol needs to talk to from being linear, as in the 2017 protocol, to being logarithmic. Okay, that's going to have a tremendous impact in efficiency. Now, in terms of guarantees or adversaries, informally, a semi-honest protocol withstands an adversary that can observe the execution of both the server and a fraction of gamma clients, that I said. And then we have this malicious variant that assumes that the key exchange that I just described is done semi-honestly. So the server honestly relays messages between clients, honestly relays public keys between clients. And from then on, once clients can speak to each other privately, then the adversary can actively corrupt the server and up to a gamma fraction of clients. And note that the server in this setting being malicious implies that it controls the communication channel, right? So it can drop messages, it can isolate clients, and so on. So that adds some difficulties in the malicious variant. Now, in terms of guarantees, I want to maybe rephrase them informally in this way by saying that from the perspective of an honest user, the semi-honest protocol ensures that their value is aggregated with at least a constant fraction of honest client inputs. And this will be very important when combining this protocol with differential privacy. And in the malicious version, the guarantee is the same, except that this constant fraction is a bit more complex. It depends on the parameters, but in a more complex way. So I'm just summarizing it using this parameter alpha here. And as we will see later, we have numerical approaches for computing this alpha, and the constants hiding in the big O here are not too bad. All right, now in terms of intuition, so let me just give you the ideas behind this protocol, which can be explained in terms of the 2017 protocol. So I'll do that. And at a high level, what happens in that protocol is that after 2 rounds in which the clients compute some correlated randomness among pairs of clients, every client submits their input, xi, this is the private input, masked with two kinds of values to the server. Okay, this is the yi, this is a submission that is done to the server. So the first mask we call pairwise mask, and it's the sum of all pairs of shares of 0 that are computed with every other neighbor. And at this point, you should think of neighbor as every other client, which was the case in the 2017 protocol, as I described earlier. And then there's also this self mask, okay, that is generated by the client and unknown to everyone else. Now, each client also secret shares among their neighbors seeds, Ki1 and Ki2, that allow to reconstruct these 2 different types of masks. And then the server receives all the Ys, adds them up, okay? And then, so now let's see what it gets. So note that the correlated masks of clients that don't drop out and send their Y, okay, they drop out before sending their Y, those cancel out, right? Because, I mean, these are common trick used in many aggregation protocols. And so this means that to recover the intended sum of xis, the server needs to remove pairwise masks of dropouts, and then self masks pollute the output in any case, and then they have to be removed for clients that do submit their Y, right? So this boils down to this decomposition where we have the sum of i's for survivors minus the pairwise masks of dropouts plus self masks of survivors. So to do a correct, the server then needs to do a correction on this sum of the y's to obtain the sum of the x's. And to do that, it requests shares of ki1 for dropouts and ki2 for the other ones, and then it can recover their masks and obtain the result. So it's crucial for security, okay, that each honest client or each honest neighbor of I will only answer a request for a pairwise mask or a self mask, but never both, okay? And the security of the protocol boils down to ensuring that the threshold in the secret sharing scheme is chosen so that surviving clients are enough to recover a required seed for correctness, and malicious neighbors of a client are not enough to recover a seed from a client unilaterally for security. Okay, so that's the idea of the whole protocol. And after this explanation, everything boils down to choosing T, choosing the threshold in this encryption. And before we move forward, I just want to say that I described the idea for the semi-honest protocol, but it's important to remark that a malicious server can lie about who dropped out in various ways. In this particular stage, when a server requests shares of one type of seed or the other, it can give inconsistent views of what happened with the submission of the Ys to clients. And this is the aspect that introduces most of the complexity in our malicious protocol variant, okay, which I invite you to check in the paper. I think is a beautiful protocol. All right, so as I mentioned earlier, in the CCS 2017 protocol, which follows this kind of high-level blueprint, the communication graph is a complete graph. And then we have to choose this threshold, but in that case, it's easy to choose, right? Because you can ensure what we need deterministically by choosing T to be less than the minimum number of surviving clients, because we want correctness, we want to obtain the sum as long as more than one minus delta n clients survive. That is on dropout. And for security, we just ensure that the threshold is more than the total number of malicious clients. Now, in the 2020 paper that I'm describing here, we instead use a random regular graph as the communication graph with n clients and k neighbors, and log n neighbors per client will be enough. Okay, so we have to translate this conditions on T from one setting to the other intuitively. So how does that go, and why a logarithmic k is enough? So if you look at the distribution of so the intuition, let me just describe the intuition, which is simple. So what we would have to show is that the threshold T is definitely larger than any number of malicious neighbors that a client might expect with high probability, and this is shown here in blue. This is a hypergeometric distribution, which is the distribution followed by the number of dishonest neighbors of a client. And we also want to make sure that that threshold T is definitely smaller with high probability, or the probability that corresponds to the correctness parameter, than that's smaller than the number of surviving neighbors, which is shown in orange here, and follows also a hypergeometric distribution. And then since hypergeometric distributions are concentrated around their mean, a logarithmic number of neighbors instead of a linear number of neighbors as in the 2017 version will be enough to satisfy the requirements.
Sorry, Adria,
okay, so this.
Sorry, Adria, can you specify something? Are the neighborhood chosen in advance, or the parties are choosing their neighbors?
That's a very good question. So that depends on the protocol variant. In the semi-honest variant, it's okay for the server to do that. In the malicious variant, the clients do that.
Okay, so they could choose. So, and you're proving that login is enough. So you're gonna have
Yeah,
some
in both cases enough.
Okay. Thanks.
Sorry, go ahead. I'm not sure if you want to ask something else.
I can ask at the end. Thanks.
Okay. So yeah, that's a good question. I don't want to get into that, but we have a more efficient structure of the graph for the semi-honest variant, and for the dishonest variant, clients have to choose themselves without relying on the server, and you have to pay a factor of 2 or so in K, but still logarithmic, and still good in concrete efficiency. So that observation, to some extent, gives us hopefully convinced you that we now have constraints that are probabilistic, and that K or the log n is enough to satisfy the requirements given a statistical security parameter sigma and a correctness parameter eta. So that's the idea. Now, in terms of asymptotics, I won't say much here, but other than that, an n turned into a log n, which improves everything you can see in the table, going from the first row to the second row. And in particular, I want to focus on client computation here. So this times n times L client cost was kind of a limiting factor. And we turned that into essentially an L log n, sorry, an L log n, where L is the length of the input vector. And that kind of changed the whole bottleneck in this protocol, essentially. So the malicious case is similar. So we managed to protect against attack where the server gives inconsistent views of who dropped out to clients. And we did that only using polylog and communication per client. Again, I think that's a beautiful part of that paper, and I invite you to take a look. But yes, we only have an extra log square and factor, and that's related to Antigone's question. All right. In terms of, so even if the analytical bounds for number of neighbors and threshold that follow from the observation that I gave you are pretty good, one can make the observation that for concrete parameter settings, one can just find this KNT numerically, and that boils down to essentially a series of queries on the CDF of a hypergeometric distribution. And just to give you an example of how good the constants inside the big O notation that I'll show you are, with 500 neighbors per client, we can handle instances with number of clients up to and over a billion clients, while the CCS 2017 paper needed, of course, about 1,000 clients, 1,000 neighbors for an instance with 10,000 clients. Okay, so these improvements are really dramatic in terms of client computation. Now, to give you another data point in terms of concrete efficiency, with 1 million clients at 5% dishonest clients and a maximum of 30% dropouts, less than 100 neighbors are enough. And yeah, as I said earlier, we can go over 1 billion clients in terms of client computation. And in the malicious variant, in a similar setting with 10,000 clients, 600 random neighbors per client are enough to ensure that to every honest client that their value is aggregated with 4,500 honest clients. Okay, so this is the guarantee that you end up giving to the client that is the user in this protocol. And I also mentioned earlier a secure shuffling primitive that is also present in the paper, which Kaylee will discuss next. And then I'll conclude now this section of our joint talk. And I'd like to say that as we get closer to the cost of computing in the clear, which is to some extent happening in this kind of protocol, the crypto stops being a bottleneck. So client computation is not a bottleneck anymore, for example, and all of a sudden, issues around good systems design, like load balancing, handling of dropouts, parallelization, and so on, become like a pressing issue to scale this protocol. So, and I believe this is the case after this work, right? So we had the crypto being the bottleneck, and now it stopped being the bottleneck, which is a very satisfying thing to say from a cryptographic point of view, I think. So I wanted to share that here. And that's it from my side. I'll pass it on back to Kaylee.
All right, thanks, Adria. So we just heard about secure aggregation at scale, where scale is taken to be the number of clients that we could work over. But one of the things we discover is once you start thinking about, oh, what can I do with millions or hundreds of millions of clients, the kinds of models that people start wanting to train get much larger. With all of those clients, you get a lot more data, and there's a lot more nuance that you can hope to extract from that data privately, while in order to provide better user experiences. But to get to that nuance, you often need more parameters in your model. Those parameters show up in a bunch of different ways. So you end up seeing very large models that end up having often a sparsity to them. So a couple ways that you can end up finding yourself in a sparse setting with federated learning is if one big class is embedding-based models. So these are things like you're trying to train a natural language model, and you have a layer in your neural network where there is a set of parameters associated with every word. And those parameters will only be updated by a particular user if that user has had experience with that word. Similarly, for an object recognition model, you might find yourself with a set of parameters for each object you're trying to recognize, and those parameters might only be updated if you've observed that object. Another class of large sparse models that we see are compound models, where you have multiple copies of some smaller model. So you might have a copy of a model for, say, each location or each company or some other set of items in a domain, and you want to conceal in a private setting which domains which items in the domain a particular user interacted with, but still train an individual model for within each of those domains. Similarly, you might think of trying to train a model with genres or clusters of data or other pluralistic models. Finally, we've been talking mostly about learning in this context, but there's another large scope of federation that we're interested in, which is analytics. This is the idea of, instead of trying to train a large neural network, for example, instead trying to compute things that you might expect to compute from, say, an analytics query. And this arises very naturally when you start to think about the task of, say, an ML engineer who needs to understand how is their model performing either before release or after release, or other fundamental characteristics of the data set that they're working with outside of the process of specifically training the model. So in those settings, you might be trying to, say, extract a histogram from some set of data, and each user only contributes to a small number of cells within that histogram, another example of sparsity. So when we think about the federated learning setup in the context of these sparse domains, we think about federated learning where we're taking the current version of the model, bringing it to device, computing an update on device, and then aggregating across a large number of devices. But if a particular device only has a very small amount of data relative to these large sparse models, it's likely the case that that data is only relevant to a small piece of those large sparse models. So what we really might want to do is download just the part of the model that this device has data that's relevant to it, update just that part on device, and then do an aggregation across all the devices that have sparse updates going into a full model size update on the server. So we want sparse sliced model download, and sparse aggregation. And of course, the choice of which slices of the model a particular device is going to interact with depends on what data is on that device. And so really what we want is private versions of both of those functionalities. So on the private sliced model download, this corresponds naturally to the private information retrieval domain, which is most likely familiar to many of the folks in this room, so I'm going to move quickly through it. The idea is that a device can download one of a set of files from the server, and the choice of which file to download remains private to the device. So in this case, we can think about each of the slices of the model as a separate file to be offered via private information retrieval. And you can kind of think about a vector where each element of the vector is one of these model slices. And then the device can form a query, which is a one-hot vector with a 1 corresponding to the model slice that it wants to download, encrypt that query using a homomorphic crypto system, and then the inner product of that query vector with the vector of model slices is an encryption, all of that inside a homomorphic crypto system, where only the device has the key to decrypt the result. The server never gets to learn anything about which slice was downloaded. So that's a rough schema for how we can do the private slice download for these models. Turning to the sparse aggregation side of things, as Adria alluded to earlier, one of the ways to go after this problem is to think about it as a shuffling problem instead. There's actually several ways you could go about this, but for brevity today, I'm just going to talk about the shuffling version. So when one interesting thing you can do is use the secure aggregation protocol that Adria described earlier to bootstrap a shuffling protocol. And the idea here is you could imagine taking a vector that has message-sized slices, where our messages here, you might think about them as roughly a particular model slice. And so we take a vector where the slices, or where the slots are the size of whatever update the device is trying to send. And each device is just going to choose a random slot to put their message in. And you might hope that if you have a large vector, that the devices will choose, even with independent choice, they will just happen to luckily choose random spots that no one else has chosen. And at least most of those messages will get through. And that's a simple way to start. But unfortunately, due to the birthday paradox, it turns out that even for quite large vectors, you end up getting quite a lot of conflicts very easily, very often. So there's actually a more clever thing that you can do, which is to build off of invertible Bloom look tables. So now what we're going to do is have each of our client devices first choose a random pseudonym, so just a random identifier for themselves. And we're going to use k-hash functions, where we take the hash of the pseudonym under each of the k-hash functions, and that selects a slot in our vector that the devices are going to place their messages into. So each device is going to place k copies of their message, and every time they place their message, they're actually going to concatenate it with their pseudonym as well. So you end up with pseudonym message pairs going into k randomly chosen slots in this vector. So on the surface, you might say, well, you just made the problem worse because now you're putting bigger messages into these slots and you're putting k copies into the slot. Haven't you just made it more likely to get conflicts out of any particular size vector? But what you can do is, for some slots, it is likely that there will be a single unconflicted copy of the message in there. And you can pull all of those out, recovering both the message and the pseudonym that was used to choose the placement of those messages. Once you have the pseudonym, the server also knows the hash function that all of the devices were using. So it can take those hash functions and the pseudonym and figure out all of the places where those messages were placed in the vector. It can then remove a copy of all of those messages. Remember, these were all aggregated using secure aggregation, essentially adding them together. So the server can just subtract off all of the copies of the pseudonym message pairs from the vector. And what you end up with is newly deconflicted slots. So now you can go back and repeat this process and keep repeating it, pulling out more and more messages until either you've extracted all the messages in the vector or you can make no more progress. And the interesting thing here is that if you follow this process and you use, say, 3 copies or 3 hash functions, a vector length of approximately 1.3 times the total number of messages you're trying to transmit works out to give you a nearly complete confidence that you're going to recover all of your messages perfectly. So from here, I'm going to hand the talk over to Peter to talk about how we can use those primitives to build into distributed differential privacy.
All right, thanks, Kaylee, and hi, everyone. Let me just hit the present button. OK, so well, in this last part of the talk, we're going to see how we actually can do distributed differential privacy at scale. And let me remind you, as Kallista said in the beginning of the talk, there's several ways in which we can distribute trust. In this part of the talk, we're going to focus on building a distributed system of differential privacy on top of a cryptographic protocol, which is secure aggregation, which Adria talked about. So secure aggregation is a complex protocol. Adria walked us through some of the details of how to make it efficient in its scale. But for the rest of this talk, we're going to think about it as a closed box that performs integer modulo summations. This is just going to simplify the analysis and the explanation. So just think about it as an integer modulo box. All right, so one might ask, well, why don't I just add Gaussian noise locally? I add small little Gaussian noise on each device, and then I rely on the fact that I'm going to sum all these shares of Gaussian noise to get the amount of noise that I need on the server. Wouldn't that work? Anyway, I have the secure aggregation box. Now, there are multiple flaws in this thinking. The first of which is that, as you recall on the previous slide, secure aggregation itself does integer modulo arithmetic. So we cannot just think about these continuous distributions, such as continuous Gaussian or Laplace. So we need to discretize the data in a clever way. And this cleverness is interesting and important because we don't want to inflate the sensitivity of the query. And I'll talk about it a little bit later on. And we cannot add continuous noise. More importantly, communication and federated learning ends up being an important bottleneck in practice, especially as we scale to these large models with millions of parameters. We want to use as little bits as possible to transmit each coordinate of the model. And we don't want this communication bandwidth constraint to mess with our DP guarantee. And once we start talking about this discrete mechanisms, such as randomized response and rapport and others, if you are familiar with these mechanisms, it's just really difficult to analyze the sum of these mechanisms precisely, especially in high dimensions. So we need something that somehow we can either analyze the sum exactly or approximately, but in high dimensions and very accurately. We also want mechanisms that allow us to give a Renyi differential privacy guarantee or a concentrated differential privacy guarantee because we want to do budgeting. We're going to run this process for thousands of iterations to train a high quality model. So we want to be able to track the privacy budget in as tight of a fashion as possible. And finally, we want to be able to sample from this noise on the device very efficiently and exactly. We don't want somehow to have to do floating point operations because we don't usually have access to those, or they might mess with the DP guarantees. All right, so with all those challenges, let's look at how we can build a distributed DP system. So as you can see on this slide, there are so many different steps involved, and I'm going to walk you through these steps one by one. But first, this vector xi that I'm showing on the leftmost side of this slide is representing the model update on each device. So think of this xi as a high dimensional vector representing the model. And we're going to be agnostic to the optimization process that happens on the device. So how you arrive to this xi is not relevant for this talk. Maybe you're running an optimization routine or computing a sketch of some sorts. All right, so the first step is we clip that vector. And this is a typical process that's done in DP-SGD in order to bound the influence of that client and bound the sensitivity of the query. So this just ensures that the L2 norm of this vector is less than or equal to some constant C. So that's nothing new, hopefully, to anybody. The second step is something new, which we call flattening, where what we do is we multiply by a random unitary matrix. So think of this random unitary matrix as a rotation matrix. And the job of this rotation matrix is to spread the energy of all the coordinates equally across the entire vector. You can see the small drawing on the right-hand side of this slide, showing you a vector where some of the coordinates are large, others are small. After we rotate, we get roughly values that are within the same range. So the idea here is when you do these kinds of rotations with high probability, you're going to get entries that are in a range that you know precisely. And these entries end up being sub-Gaussian. Now, from a practical perspective, how do we do these rotations? Because this means we need to allow to multiply the vector by a large matrix. How do we do them efficiently? There are many ways. The randomized Hadamard transform has the properties we're looking for. And the randomized discrete Fourier transform also gives us those properties of ensuring that the coordinates are in that range that we want. So we're still operating on floats. And the next step is to go from floats to integers. So this is the discretization step. And this step has two sub-steps. The first one is scaling. So we need to multiply by some constant s, which we're going to take to be 1 over gamma. So keep that in mind. And this scaling stretches the signal, essentially. And when you stretch the signal, what you are doing is you're trying to reduce as much as possible the rounding errors or the quantization errors. For instance, if you have a value of 4.2 and you multiply by a scale of 10, you get 42. And then now if you round to the nearest integer, you don't get any error because you've scaled by a factor of 10 already. So anybody who has done quantization in the past knows that precision or scaling is important for accuracy. It's going to also end up helping for DP and you'll see that in a bit. So after we scale, we do the rounding, and one method to take here is to do randomized rounding, essentially round to the nearest integer with a probability that's proportional to how close you are to that integer. Now, it turns out that there's a problem with randomized rounding. It's not a big problem, but it's a subtle, small problem, which is when you round the vector to the nearest integers probabilistically, the L2 norm of this vector is going to get larger. And this is not cool for DP. Probably you guys know that for DP, you need to control the sensitivity of the vector. And with randomized rounding, what happens is that the L2 sensitivity, or the L2 norm of the vector, grows up by a factor of about root d. You can show that, where d is the dimensionality of the vector. So that's not very cool. So what we do is we can analyze a high probability bound on what's going to happen to the norm of the vector upon this randomized rounding. And what we could do is we could do something called conditional randomized rounding, where when we round, we check the L2 norm. And if it is above this high probability bound that we have, we essentially redo the rounding again. We ignore that step, and we redo it again. And we can show that if you do it a constant number of times, you're going to succeed with very high probability. So this is easy to see. And this allows us to actually round to something very close to c squared, which is the norm that we clipped to at the beginning. You can see this extra term here in the blue box. It has this gamma, and gamma is something really small because we're going to scale to something large. Keep in mind that s is equal to 1 divided by gamma. So gamma is the rounding granularity. All right, so once we manage to do this conditional randomized rounding step, we now have a proper bound on the L2 norm of the vector, of the rounded vector. So now we have an integer vector, and we have a proper L2 norm bound on it. And that L2 norm is hopefully not too far from the L2 norm that we clipped to at the very beginning, which is good. So now we have integer data with a proper tight bound on its L2 norm. So this is now the very important step for DP. We need to add noise, and we need to add integer noise. So for this talk, we're going to use the discrete Gaussian noise. And let me try to tell you what the discrete Gaussian noise. Hopefully, a lot of the crypto people are familiar with it because it's widely studied in the lattice crypto community. So discrete Gaussian is just the discrete analog to the continuous Gaussian. As you can see, it's essentially like the PDF of a Gaussian, but now we form a PMF from it. So the normalizing constant is a little different. And in a recent paper that appeared in NeurIPS of last year, it was shown that this mechanism essentially has a performance that is very close to the continuous Gaussian mechanism. So all those interesting Renyi DP and concentrated DP guarantees that you can prove for the continuous Gaussian mechanism, they carry over almost unchanged to this integer version of the continuous Gaussian, which is pretty cool. But there's a problem when we apply it in a distributed setting. Because when we apply it in a distributed setting, we need to now analyze what happens to the sum of such discrete Gaussian variables. And it turns out that sums of discrete Gaussians is not a discrete Gaussian. So this was, at least to me, a surprise, because I'm not in the lattice crypto community. I always thought sums of Gaussians is a Gaussian, and I thought that intuition is going to carry over from the continuous space to the integer space, but it turns out that they're not actually a Gaussian. When you take a bunch of discrete Gaussians that are independent, you sum them up, you're not going to get a Gaussian or a discrete Gaussian. But what we were able to show is that if you look at the max divergence between the sum of two discrete Gaussians, and you measure that divergence between that sum and a discrete Gaussian that has the sum of the variances, that ends up being really, really small. So for instance, I'm showing you an example on this slide. If we choose the variances to be 3 for each of x and y, the two discrete Gaussians that we're going to sum, then the divergence, max divergence between them and a discrete Gaussian that has the variance being the sum of the two variances ends up being less than 10 to the negative 12. So we know that even though the sum is not a discrete Gaussian, it has to be extremely close to the discrete Gaussian. In fact, this max divergence bound that we derived, you can extend it to high dimensions. You can do lots of things with it. And then you can use it to arrive to a proper DP guarantee, which I'm showing on the slide. And this is a concentrated DP guarantee. You can view it also as a Rennie differential privacy guarantee. The one thing that I would like to highlight about this result is that if you look at the epsilon that I'm showing in the box on the right-hand side, you'll see the first term is this norm squared divided by n times sigma squared. This is exactly what you would get under the continuous Gaussian mechanism. So this first order term matches exactly the continuous Gaussian mechanism. But there's now an extra penalty term, which is this tau times d, or tau times root d, if you want, term. Now, d is very large. This is the dimensionality of the model. So think about it as something like 1 million or 5 million parameters. So it's really large. But tau ends up being extremely small. I'm showing the expression of tau in the box as well. And it turns out that for all intents and purposes, tau ends up being something like 10 to the negative 16 or 10 to the negative 19. So it's a very small parameter. And it's smaller as we scale the data more and more. So if the granularity it gets smaller and smaller, this tau gets even negligible. So this tau times root d, you can essentially ignore it. All right, so now that we've added integer noise after we discretized, we get essentially values that are unbounded. Those are integer values, right? And so we still need to do something in order to use the secure aggregation protocol, because the secure aggregation protocol operates on a finite group or a finite field. So depending on our communication cost, say we want bits per parameter or per coordinate, then what we can do is we can compute the field size of secure aggregation. It ends up being 2 to the power that. And then we can use this to determine how much we can scale the data. Ideally, we want to scale the data as much as possible in order to ensure we get DP guarantees close to continuous Gaussian, and in order to also avoid these rounding errors that we talked about. But we cannot scale it beyond a certain point, because if we scale it beyond a certain point, then we would be modulo wrapping around with high probability. So we want to balance out these two events. And in the paper, we show precisely for a given bit width how you can choose a scaling parameter in order to balance out these two types of error events. All right, so with that, I can show you at least one set of experiments. In the paper, we have a lot more experiments that you can take a look at. So this is the Stack Overflow data set. It's one of the biggest federated learning benchmark data sets. We are training here an LSTM for a next word prediction model. And this model has, I believe, more than 5 million parameters. So it's a very large model. And the data set itself has more than 342,000 clients. So again, it's a pretty large data set. And on the left-hand side, the figure that I'm showing you shows the performance of this distributed discrete Gaussian method that I just presented for a variety of values of bit widths, communication costs. And you can see that for 12 bits, it doesn't work, especially for smaller values of epsilon. The accuracy that we get is very, very low. But as we move to 14 bits or more, the accuracy of this DD Gauss, distributed discrete Gaussian, starts matching exactly the continuous Gaussian mechanism. So in other words, what this figure is suggesting is that with about 14 or more bits, 16 or more bits, we could get the exact performance of continuous Gaussian while giving provable privacy guarantees under secure aggregation. And this is all, again, distributed DP. The figure on the right-hand side does something a little different. It goes over a number of noise scales. Z here is how much noise you're adding locally. So it really determines the noise scale. And it does it with 1,000 clients per round. And it shows you that if you have a bit width about 18 bits per parameter, you're going to always match the performance of the continuous Gaussian mechanism. So if you have a lot of clients per every secure aggregation round, every round of federated learning, you need about 18 bits. And you're going to be able to train this large model of 5 million parameters. All right, so this slide, you may remember it from the beginning of the talk, where Kallista was saying that we need a privacy in-depth analysis where we give some DP guarantees to the server, and those DP guarantees get stronger and stronger as the surface of attack gets bigger. This is essentially what we've managed to do in this work, where for the server, we're giving some DP guarantee as long as the server is honest but curious or semi-honest. And we cannot give the full privacy guarantees because it's hard to prove or provide the secrecy of the sample. We're doing amplification via sampling here. This is an open question of how to actually strengthen those guarantees. But then for the released model or at deployment, we give stronger guarantees that match the central DP ones. All right. In the last 1 or 2 minutes of this talk, I'm going to quickly go over some challenges and some opportunities. So hopefully you'll find this useful. The first thing is I want to say that, and hopefully this is not a surprise to anybody in this room, privacy is multifaceted. So it's not a binary quantity. We cannot just say this is private or not private. And what's fascinating about it is that we need to understand tensions between privacy, communication cost, computation, accuracy, and sparsity, as Kallista mentioned. So these trade-offs are perhaps studied separately, but they're not studied jointly. So there's a lot more work to couple all these trade-offs and understand how they interact together. There's a lot of tension between privacy robustness and fairness. And one way in order to relax or ease that tension is through personalization, which we didn't touch on in this talk. So hopefully maybe another time we can talk about how we can do model personalization on device in order to ease out the tension between differential privacy and the other things such as fairness and robustness. And cryptographic techniques, which we saw in this talk, are going to play a critical role in strengthening privacy and giving stronger guarantees. Now, one important thing is that DP, and I didn't really dwell too much on it in this talk, ends up almost always hurting the accuracy quite a bit, especially if you want to get DP with small epsilon, something like 1 or even smaller. And so the question becomes, how can we mitigate the effect of differential privacy? Now, obviously, if you have very large populations, tens of millions or hundreds of millions or even billions of clients in the system, you can offer such strong DP guarantees. But in order to offer such strong DP guarantees and get good accuracy, you would need to run on larger cohorts, so have more clients per round and perhaps do more rounds. So the trade-off here becomes not privacy versus accuracy, it becomes privacy versus communication or privacy versus computation. So we need to know if we want to pay a penalty, it shouldn't be a penalty in the accuracy, it should be a penalty in other resources, hopefully, that we can afford. And we still don't have very good privacy budgeting and management systems to allow us to track the privacy across multiple models that we train on the same population of clients. So we look forward in the next few years for a development of a nice privacy budgeting and management systems. And finally, one of the areas that we believe are going to help in ensuring DP is deployed at scale in practice is the use of public data, because there's a lot of public data, and for that data, we don't need to enforce DP. So how do we actually combine the availability of large public data sets with private data sets in order to give better privacy accuracy guarantees? And also, how do we use the fact that a lot of these models are either sparse, and sparsity will help with accuracy, or they can be projected down onto a much smaller, lower dimensional space. All right, so if you want to learn about all these challenges, you can either take a look at this paper that has been around for more than a year now. It's called Advances in Open Problems in Federated Learning. We've updated it recently, and it got published in Foundations and Trends in Machine Learning. And we have very recently put another paper up with so many great co-authors. It's called The Field Guide to Federated Optimization. This last paper is focused on optimization. So it still touches on privacy and other aspects, but the focus is on purely optimization. So with that, I'll thank you, and we'll be happy to take questions.
Thanks a lot to all of you for the very interesting talk. I have a lot of questions, but for the interest of time, let's first see the audience questions. I can see that you have answered most of them in the chat. I think there's one
13 hours.
from Vinod that you didn't ask. Vinod, do you want to answer your question live?
It's okay. Actually, we can do it afterwards, or I can just sort of see the answer on chat. That's fine.
Oh, okay, great. So, is there any other question from the audience? I can ask a quick one in the meantime if somebody has a question. I wanted to ask if you are thinking of full malicious security for your aggregation protocol. Are you thinking of it? Are you interested?
So full malicious meaning more than what I presented, in the sense that protecting also in the key distribution phase?
Or like, for example, that the secret sharing is not done correctly, that the parties are sending different things, different shares, like there was some noise from my background. I mean, like during the protocol as well, during the online phase, for example, if the secret sharing is not done correctly from the client side.
Yeah, that's covered by our malicious protocol. So that's handled. You don't need verifiable secret sharing or anything like that in this particular setting.
So you offer full malicious security.
Yeah, as long as the key distribution phase where clients exchange public keys with each other through the server in a pre-computation phase is done semi-honestly by the server. If that's the case, then we have full security in the sense of full security with a word, malicious security with a word.
Okay, nice.
And unfortunately, when we're working with very large numbers of clients like we see in the real world, we don't have any public key infrastructure to appeal to. So it's really hard to work around the need for that initial trusted step.
Right. And about practice, do you have like these protocols in practice at Google?
Yeah, we do. We've been running the 2017 protocol for many years and experimenting with the extended protocols.
Nice. So,
can I ask a question unmuted? I'm sorry. Yeah, Adria?
Yeah, please go ahead.
Adria, it's a question for you. So you mentioned that your protocol is statistically secure, and I understand this because of this arrangement that you're doing, this random sampling for assigning the parties. I wonder if you're considering other ways of getting logarithmic communication and so on without this assumption.
I've not thought about that. I wouldn't know how to go about it. So you're asking whether one can get logarithmic communication per client, or more generally polylog overhead for secure aggregation without a statistical security argument?
Yeah, I think something similar to the results you already have, but yes, exactly, without relying on static corruption.
Oh, okay. So you're asking whether we could drop the assumption of a non-adaptive adversary.
Yes, exactly. Sorry, that's what I meant. Yeah.
Okay, I see. So let me rephrase then. So the question is, can we get logarithmic communication per client, or more generally logarithmic overhead with against adaptive adversaries? And I don't have an answer. I don't know either way. Sorry. Or not sorry, depending if you're working on that.
No, it's okay. Just, but like, does it seem relevant? Because at the end of the day, it's like a short time frame where you can corrupt and so on. So it's probably not that relevant in practice.
I'm very satisfied by in this case with I mean, I'm happy with assuming a non-adaptive adversary, but particularly I think it's realistic and fine. But I mean, theoretically, your question makes a lot of sense, and it's fair. It's a good question, I think.
Understood. Thank you.
Great. So another question like the last one. Let's make it quick. Somebody, Amit Akarwal, is asking: is there any cryptographic components in the protocol other than the initial PKI? What other assumptions do you have?
So we need authenticated encryption, right? These clients need to talk to each other through the server. We need signatures, right, for the malicious variant to essentially make sure that claims by one of your neighbors do belong to them. But no fancy assumptions. It's just all quite standard. We instantiate the random oracle model with AES. I don't know if that answers the question. I hope so.
Yeah. There's some Diffie-Hellman agreement and some expansion of a seed with a pseudorandom number generator, but it's fairly straightforward.
Great, thank you. Thanks a lot, guys. We can get other questions offline. Thank you so much.
Thank you.